Welcome to this deep dive from TargetSeal.
We're glad you could join us today.
We are TargetSeal Incorporation, a Canadian company really dedicated to providing high-quality sealing solutions.
That's right. And we're proud to serve as the authorized distributor for top-tier manufacturers like Durlon and Sepco right here in the Middle East. We see firsthand how absolutely crucial reliable seals are.
Exactly. And today we're focusing on, well, what seems simple but is vital, keeping things sealed tight when the heat is really, really on.
Yeah, think high-temperature industrial applications.
It's not just about stopping drips, is it? Think refineries, power plants. These are critical industries.
Absolutely critical. A failure there, it can have massive safety consequences, not to mention efficiency losses.
So our goal today is to understand why is it so hard? Why is achieving a reliable seal under extreme temperatures and often intense pressure, too, such a big engineering challenge?
It really is. And then we'll explore some of the solutions that are out there.
Good. Because environments like, say, gas turbines or heat exchangers, they put incredible stress on sealing materials. Right?
Immense stress.
So let's pack that. High temps, high pressure. What makes that combination so tough for a seal?
Well, okay, when you crank up the heat, the materials we normally rely on, they start acting differently, less predictable.
Also,
They expand naturally, but maybe not evenly.
yeah.
They lose their stiffness, become less springy. That makes for a weaker barrier.
Okay.
And then you've got chemical changes happening within the material, sometimes even losing actual mass. The material literally disappears over time.
Wow. That's a lot to deal with just from heat.
And then you throw high pressure into the mix. It's constantly probing, looking for any tiny weakness, any microscopic gap in that seal.
Amplifying the stress.
Totally.
Oh.
It just makes everything harder. Imagine an exhaust manifold in a refinery, or maybe some chemical processing equipment, a failed seal there. That's serious downtime, potential hazards. It's a big deal.
Absolutely. We're talking temperatures way beyond our everyday experience. You mentioned Durlon's data. Gives us some perspective on limits.
Yeah, it does. For instance, phyllosilicate, which is a type of mica that can apparently go up to around 1,000 degrees C. That's, 1832 Fahrenheit?
Pretty impressive heat resistance.
Very. Then you look at flexible graphite. That's more in the range of 450 Celsius, maybe 850 Fahrenheit, generally speaking.
Okay.
And compressed fiber sheets, usually around 400 C or 750 F.
So those numbers really show why you need special stuff when you push things that high.
Exactly.
Which brings us neatly to some of these innovative materials. Let's start with that phyllosilicate you mentioned specifically. Durlon's HT1000. What's the story there?
Right. HT1000, it's definitely a go-to for really high heat.
What makes it tick?
Its base is something called phlogopite mica paper. It's a specific kind known for heat resistance. But a really critical part is the binder, the glue holding it together, essentially.
Oh, that binder.
Yeah. And Durlon apparently uses way less of it, like less than half compared to some other products out there, especially those using vermiculite-phyllosilicate blends.
Less binder. Why is that good?
Well, it means it holds on to its weight much better when it gets really hot. Tests show HT1000 loses less than 4% of its weight, even at 800 degrees C. That's nearly 1,500 Fahrenheit.
And why does holding on to weight matter for sealing long term?
Ah, good question. See, if a gasket loses a lot of mass because of heat, it can't maintain that clamping force, that pressure on the flange faces.
It shrinks, basically.
Effectively, yeah.
Right.
Or compresses more easily. It leads to creep, and eventually the seal just isn't tight anymore. It starts leaking. So left weight loss, that directly means a more durable, more reliable seal over time in those hot conditions.
Makes sense.
Plus, HT1000's been lab tested for fire safety. It's non-combustible, which is, pretty important.
Crucial, I'd say. And it might be a more sustainable option, too.
That's mentioned, yeah. And it comes in a few different styles, depending on the need. The basic one is S90, just the mica paper and binder. Then there's O316, that adds a thin stainless steel layer, 316 grade, inside for strength.
Right, bit more robust.
And then T316. That uses a perforated stainless steel carrier. The holes give it a bit more flexibility, helps it conform better to maybe slightly uneven flange surfaces.
Interesting. So you've got options depending on the mechanical demands. And the mica itself, this phlogopite mica, it has good properties on its own.
Oh, definitely. Phlogopite mica is naturally non-toxic, which is great.
Yeah.
It's also surprisingly flexible for a mineral, has high tensile strength, resists chemicals well, and it's inherently fireproof.
Quite the package.
It really is. Makes it ideal for these tough industrial sealing jobs.
And importantly, thinking back historically, it's a good alternative to asbestos.
A very important point. Huge safety and health implications there.
Okay, let's shift gears a bit. Flexible graphite. You mentioned Durlon's Sigralex APX2 and these ETG extreme temperature gaskets. These are for even higher temps, like above 650C, 1200F.
Generally, yes. That's where the ETG concept really comes into play.
So what is the concept?
It's actually quite clever. See, at those really extreme temperatures, just keeping enough bolt load, enough clamping force on the gasket gets tricky. Materials expand, relax.
Right.
And while flexible graphite seals incredibly well because it's so conformable, it doesn't love oxygen at very high temperatures. It can oxidize, burn away slowly.
Ah, okay. So a potential weak spot.
Exactly.
Yep.
So the ETG design tackles this head on. It combines an oxidation barrier, guess what? Our friend, the high-temp HT1000 material, with the sealing power of flexible graphite.
Wait, so the HT1000 acts like a shield protecting the graphite?
Precisely. It forms a protective layer around the graphite core. This lets the graphite do its main job, creating that super tight seal and maintaining bolt load without oxidizing away so quickly.
That's smart, using each material's strength.
It's a synergistic approach.
Yeah.
And the graphite itself, the Sigralex APX2, is important too. It's homogeneous, made from expanded natural graphite. And critically, it doesn't have adhesives or binders mixed in.
Like we talked about with the HT1000 binders.
Exactly. Those binders can break down at high heat, contributing to oxidation. So being binder-free helps APX2 resist oxidation better.
Okay, this layered approach, using different materials for different jobs, seems key. Now, the sources also bring up Compressed gaskets. They can use either HT1000 or this ETG setup. Tell me about those.
Right, Compressed. They have a neat mechanical design. You start with a solid metal core, usually stainless steel, and machined onto both faces are these concentric sort of wave-like grooves, serrations.
Okay, I can picture that. Grooved metal.
Then you apply a soft, high-temperature sealing layer over those grooves. That layer could be HT1000 or it could be one of these ETG layers we just discussed.
So you get the strength of metal plus the sealing of the soft layer.
You got it. And those grooves, those serrations, do something important. They concentrate the bolt force onto the peaks.
Ah, like high heels on a soft floor, higher pressure.
Exactly. Creates a really high sealing stress right where you need it, meaning you can get a tight seal with less overall bolt force.
And I bet that solid metal core helps against blowouts.
Hugely resistant to blowouts. Very stable. Plus, they're generally easier to handle and pop into place compared to some other high-tech gaskets. Often a good choice when you need top reliability without cranking down bolts excessively.
Makes sense, especially if controlling bolt load is tricky.
Now, related to that, there's another type called Durta ETG gaskets.
Durta. How are they different?
Slightly different internal construction. Instead of just machine grooves, they use a specially engineered metal core. And the soft layers, the graphite in the ETG version, are chemically bonded to this core.
Chemically bonded. Sounds strong.
It is. And the big selling point is that this core is designed to be uncrushable. It doesn't compress like older designs with corrugated metal inside might.
Uncrushable, so it holds its shape no matter what.
Pretty much under normal gasket loads. This means it seals really well even with lower bolt loads. Great for high temp, high pressure pipelines, vessels, exchangers.
Versatile.
And again, excellent blowout resistance, fire safety, good chemical resistance too. It's another advanced option.
Amazing how many variations there are, all tailored for these tough conditions. What about really big flanges? I saw something about an HT1000 paste.
Yeah, that's a practical solution for making huge gaskets out of HT1000 sheet. Trying to cut and handle one massive, maybe fragile gasket is tough.
I can imagine.
So instead, you cut it into segments, often with interlocking dovetail joints.
Like puzzle pieces.
Exactly like puzzle pieces. Then you apply this special HT1000 paste into those joints as you assemble it.
And the paste seals the joints.
Right. When it cures, it basically makes the whole segmented thing act like one continuous leak-proof gasket. It just makes manufacturing and, maybe more importantly, installing those really large diameter high-temp gaskets much more feasible.
That's really clever. Solves a logistical headache. Okay, materials designs. But how do we know they work? Especially with fire risk. That brings us to testing, like API 6FB. What's API and why this test?
Okay, API is the American Petroleum Institute. Major standard-setting body for oil and gas, globally recognized. Their standards are like the rule book for safety and performance. And API 6FB. That's a fire test. A really tough one, specifically for flange gaskets used where fire is a serious risk, like in oil and gas facilities.
Makes sense. And there are two types, type 1 and type 2. Onshore versus offshore?
That's right. The basic idea is the same for both. You bolt up a flange joint with the gasket you're testing, you pressurize it. Then you blast it with flames for an hour.
An hour under fire and pressure. Ouch.
Yep. Then you let it cool down, release the pressure, and pressurize it again. All the while, you're measuring how much it leaks.
Okay, so what's the difference between type 1 and type 2?
Intensity. The fire intensity,
Yeah.
type 2, the offshore one, is way tougher.
How so?
It uses a single, much more powerful burner. Flame temps can hit 2,000, even 2,500 degrees Fahrenheit. Compare that to type 1, which is more like 1,400 to 1,800 F.
That's a huge jump in temperature.
It is. And they also measure the temperature near the flange itself using a special block. In type 2, that block can get up to 1,800 F versus maybe 1,200 F for type 1. It's just a much more severe heat soaking, simulating potentially worse offshore fire scenarios.
Wow. And to pass, the leakage has to stay below a certain limit.
Exactly. Throughout the whole thing, the burn, the cool down, the repressurization.
And what's that limit?
For a typical benchmark size, like a 6-inch class 300 gasket, it's usually around 24 milliliters per minute maximum leakage.
Okay. Now, Durlon's performance here seems like a big deal in the info we have. Their SWG DRRI ETG gasket. What did it do in that tough type 2 test?
This is where it gets really impressive. According to the sources, that specific Durlon gasket didn't just pass the API 6FB type 2 test, it achieved zero leakage.
Zero. Through the whole thing, the fire, the cool down, everything.
Zero leakage, start to finish, which is, frankly, exceptional.
Yeah, I'd say.
Especially since, as the info points out, many manufacturers aim for passing the easier type 1 test. Getting zero leakage on type 2, that really stands out.
Speaks volumes about the gasket's quality and engineering. And this wasn't just Durlon saying this, right? It was verified.
Absolutely. Properly verified by an independent lab, Yarmouth Research and Technology, and the results certified by a professional engineer. Third-party validation is key for claims like this.
For sure. And you have to assume this amazing performance comes back to those materials we discussed. The HT1000 and that APX2 graphite.
No doubt about it. That HT1000, with its heat resistance and, crucially, its low weight loss, holds the structure together during the fire.
Right.
And the APX2 graphite's high oxidation resistance means the actual sealing part doesn't degrade away under that intense, prolonged heat. It allows it to maintain that seal. It's that synergy again.
A testament to getting the material combination right. And Durlon didn't stop at API tests, did they? They did their own custom testing.
Yeah, they did some in-house testing too, which gives a slightly different perspective. They took a whole gasketed flange joint, the entire connection, put it in an oven, pressurized it, and cooked it at 1382 F, that's 750 C, for 24 hours straight.
24 hours at that heat. On the whole joint, that sounds tough.
Very demanding. Simulates long-term high-temp service pretty well.
How did they measure performance?
They watched the pressure inside, how much it dropped during the 24-hour heating, and also after it cooled down. Pressure drop equals leakage.
Testing the whole assembly like that feels very realistic. What did they find?
The key finding was again about the ETG design. That configuration, with the graphite protected by the HT1000 layer, leaked 14 to 17 times less than a gasket using just a standard mica filler.
Whoa, 14 to 17 times better. That is a massive difference.
Huge difference. It really backs up the idea that this ETG design maintains a much tighter seal when exposed to extreme heat for long periods.
So all this testing, rigorous API tests, custom tests, it adds up to some serious fire safety credentials for Durlon, doesn't it?
It seems so. The Durlon DRRI ETGS SWG is apparently the only high-temp gasket out there right now that's passed API 6FB Type 2 and API 6FB Type 1 and API 607, which is a fire test for valves.
Holding all three certs, that's quite an achievement. Shows real robustness. Yeah.
Exactly. Suggests it's suitable for a wide range of critical fire-safe applications.
Okay, super important point before we wrap up. There's a safety warning in the material we absolutely need to highlight.
Yes. Critical piece of advice for anyone using these high-performance gaskets.
Durlon is very clear. You should never recommend their gaskets for situations where you expect both the maximum listed temperature and the maximum listed pressure to happen at the same time, unless
a qualified, independent engineer has studied that specific application and signed off on it.
Right. Pushing both limits simultaneously needs careful, specific analysis. Don't just assume it's okay based on the spec sheet alone.
It's just good engineering practice.
Yeah.
Always get an expert assessment for those extreme edge cases. And of course, the basics always apply.
Yeah.
Ever use more than one gasket in a joint. Stacking gaskets is a huge no-no.
Right.
And always use a brand new gasket whenever you reassemble a flange. Never reuse them.
Absolutely vital safety rules. Okay, let's try to quickly recap the main takeaways from this deep dive.
All right. We've seen that sealing things reliably at extreme temperatures is Well, complex. It takes advanced materials, clever designs, and really rigorous testing.
Materials like Durlon's HT1000 mica composite and their Sigralex APX2 graphite are key players, each bringing specific properties to the table.
And tests like API 6FB, especially that brutal Type 2 offshore version, are the benchmarks for proving fire safety performance.
Durlon's results hitting zero leakage in Type 2, the ETG performing way better in long-term heat tests, really demonstrate a high level of material science and engineering.
Definitely shows a commitment to quality for these demanding jobs.
It really makes you appreciate the hidden engineering, doesn't it? All the science behind these components that we rely on to keep essential industries running safely.
You often don't think about a gasket until it fails.
Exactly. And it makes you wonder, what other fields dealing with extreme environments could use innovations like these? Aerospace, advanced energy.
That's a really interesting thought. The principles could certainly apply elsewhere.
And I guess it just shows that ingenuity is always pushing the boundaries, finding ways to improve safety and performance even when conditions are incredibly challenging.